The engineer chef planned to cook one hot entrée and one cold dessert for a customer. He told the engineer chef that he wanted his food temp to be within 5 degrees Celsius of each other. At 11 a.m., the engineer chef finished cooking and observed that the temp of the hot entrée was 50 degrees Celsius and that the cold dessert was 13 degrees Celsius. At 11:30 a.m., the chef measured their temp again, and this time the hot entrée was 43 degrees Celsius and the cold dessert was 19 degrees Celsius. Find the time until he can serve the food to the customer and which this is closer to the room temp, assuming that the room temp is 30 degrees Celsius.
First, let us identify the given. 11 a.m. T is equal to 0. So let us assign the values. We'll let A be the cold dessert and B be the hot entree. So at the beginning, at T equals 0, UA is equal to 13 degrees Celsius and UB is equal to 50 degrees Celsius. So at 11:30 a.m., when T is equal to 0.5, UA is equal to 19 degrees Celsius and UB is equal to 43 degrees Celsius. Let UO be the ambient temperature, and UO in this case is equal to 30 degrees Celsius. So now, we have to find T when the difference of UA and UB is less than or equal to 5, and which meal is closer to the ambient temperature of 30 degrees Celsius.
In this problem, we will use the formula for Newton's law of cooling, which is du over dt equals h quantity u minus u sub o quantity. Manipulating the differential equation, it will become du over u minus u sub o equals h dt. Then when we integrate both sides, it will become ln quantity u minus u sub 0 equals ht plus c. Raising both sides equation to e, it will become u minus u sub 0 equals e raised to ht plus c. Since e raised to c is another arbitrary constant, which we can substitute it to c1. So it will become u minus u sub 0 equals to e raised to ht c1. Transposing uo to the other side, it will become u equals e raised to ht c1 plus u sub 0.
Now that we've derived the formula for the general equation, we have UA equals to CA e raised to HAT plus U sub naught. Now, at T equals 0, we know that the temperature of the cold dessert is equals to 30 degrees Celsius. Now, substituting these values, we get 13 is equals to CA e raised to 0 plus 30, and we know that e raised to 0 is simply 1. Now, simplifying the equation, we were able to obtain the result of CA equals negative 17. And now we need to solve for the second constant in the equation. At T equals 0.5, we know that the temperature of the cold dessert is 19 degrees Celsius. Again, substituting the values into the original equation and substituting the value of CA, we get 19 is equals to negative 17 e raised to HA times 0.5 plus 30. And simplifying the equation, we get 11 over 17 is equals to e raised to HA times 0.5. Now, if we're going to express the equation into its logarithmic form, we get the natural logarithm of 11 over 17 equals to 0.5 HA, and simplifying, we obtain the result of HA equals to negative 0.87. Similarly, we can obtain the values for the constant of the second equation pertaining to the hot entree by substituting the values that were given to us. And as a result, we're going to get the constant for T, which is 20, and another constant for T, which is negative 0.862.
Since we're looking for the difference of the two temperatures to be 5, we'll use UB minus UA is equal to 5. So substituting UB and UA, we'll get 30 plus 20 e raised to negative 0.862t minus 30 minus 17 e raised to negative 0.871t equals 5. So cancelling both 30s, we'll get 20 e raised to negative 862t plus 17 e raised to negative 0.871t equals 5. So using shift solve, you'll get T is equal to 2.301 hours. So the customer will get this food at 1:18 p.m.
To identify which is closer to the ambient temperature, we need to substitute T for both equations. For UA, when T equals 2.301, UA will be 27.7 degrees Celsius. For UB, when T equals 2.301, UB will be 32.7 degrees Celsius. So this means that UA is closer to the ambient temperature than UB.